Introduce you Nayla Moray. She obtained her BSc in Electrical Engineering from Princeton University in 2007. In 2012, she received her PhD from the Universitat Autònoma de Barcelona in affiliation with the Computer Vision Center. Her current research interests include few-shot learning and domain adaptation.
Hello, everyone. Thanks for joining, and thanks for the organizers for inviting me. It's a pleasure to be here. So my talk's going to be all about meta-learning now. We're going to talk about weakly supervised few-shot classification and segmentation, touching indeed on meta-learning and episodic learning, but thinking really very much about how do we actually address the problem of just not having a ton of data, right? Which is taking few-shot learning even one step further. Right, so few-shot learning with episodic training. This was basically an introduction to keep everybody on the same page. You actually heard a lot about that just very recently. So I'll go quite quickly through, right? So the approach is, as Ismail mentioned, learning to learn with a few examples in which you you can simulate this approach during training time by sampling episodes from some large database that you have access to at training, right? And then each of these tasks that you simulate is an episode. So to give an example here, once again, very quickly as we just went through this. So let's look at this example here where you have a bunch of dogs that you're trying to classify into breeds. And you have 4 classes here. And then you have a query class, right? So you want to figure out, is this dog one of these dogs that you see represented by your support set, right? So you have sort of one example per class. So this would correspond to having one example per class. So L here would be 1, and then you'd have a 4-way task, right? So this is an L-way Z-shot episode where you have 4 as L, and then Z is 1. So here, the learner is going to learn to take as input this query and some of these support images, and then to generate a class membership score in some way, right? That could be often via some sort of metric learning, as was mentioned before, where you have some embeddings for the support images and for the query. You put it into some similarity function, and then you perform some prediction based on that. For example, what's the highest similarity score? That's a typical approach. So this is the approach we'll take, but we won't actually talk a lot about that. What we'll talk about is, the task we're trying to solve here, which is few-shot classification and segmentation. So this was a paradigm that was introduced in CVPR 2022 by Kang and Cho. And the aim here is to get to a more realistic scenario where you want to not just segment an image or not just classify an image using few-shot learning, but then to actually do that at the same time. And I'll explain, why that's valuable in a moment, right? So this is once again a few-shot setting, and importantly, this is a multi-label and background-aware approach, right? So what we're saying here is we are interested in a realistic setting where you may not have like a class of interest in your image, right? Your image might be completely non-relevant to the classes you want to detect, which is of course very practical and reasonable, but often, not something we see in the standard evaluation paradigms that we set up, right? So just to talk you through this very, very quickly, so just to understand the setting we're concerned with here, let's say you have a 3-way one-shot scenario, right? So you have 3 classes and you have sort of 1 sample each. In this few-shot case, what you'd have is not just the class labels per image, but also some segmentation mask, okay? And then you're given a query image, and then what you want to do is to construct a foreground mask per class, so for each of these. And for example, you see here that for the query image, there are 2 classes that actually occur in the support set, right? So you actually want to detect 2 classes out of 3, and there's one that you don't want to detect, it's not present. You want to be able to say, okay, it's not present in the image. As you see here in the class-wise foreground maps, And then you want to be able to combine this into your final segmentation result. Okay. So Kang and Cho in 2022, they proposed this integrative few-shot learning approach. And integrative in this sense means that they're combining they're solving the task jointly. And then to do this, they propose a new architecture called an attentive squeeze net. And the reason I'm going to go into that in a little bit of detail, just because there are a lot of flavors of this that will pop up in later work that I'll show on our current method. So don't be alarmed. I'm going to go through this in like a certain level of detail, at least to get the big picture. So what this method is doing, and I mean, just at a high level to back up a bit, what it's really going to do is try to leverage as much as possible correlational information between the support images that you have and the query image to really try to squeeze out as much localized semantic information as possible to be able to perform segmentation well, right? So that's like the kind of high level picture of the motivation for this architecture. But to just talk through it very, very briefly. So you're given a set like a feature map, right? Like a tensor, like a sort of like a spatial tensor. So you have height, width, and some sort of channel dimension. You have this for both your query image and your support image. Let's imagine we have one support image for now. So the query image is red and the support image tensor is blue. And so what we're doing is we're taking multiple, like sort of a feature pyramid, right, of these tensors. And that's sort of like the three you see there. That's the pyramid of different resolutions. So let's just focus on one because it naturally kind of generalizes. So if you look at the bottom, you have these two tensors, right? Like h by w by c and then h by w by c for both query and support. And then you're going to correlate them, right? So you're just going to compute a bunch of dot products between your two big tensors, and that's going to give you this sort of massive tensor of dimension, as you see there, HQ, WQ, HS, WS, etc. Right? And so basically, this is going to give you really rich. Sorry for the interruption, but we'll share screen. Oh, it says resume share. It is. It says, but it says stop share now. So it's. Maybe it doesn't see. I think it sees that. Maybe you can choose the. Sorry. Yeah. Okay. Right, and then so once you have this big tensor, from there we do a series of the authors. They did a series of steps to shrink that big tensor into one that's actually a dimension you want. So it's just a series of transformations and projections, and I won't go into a ton of detail, right? But the key thing here to remember is that this allows to extract a lot of rich localized information, which is really key for the segmentation task that we're interested in. So the advantages of this approach, so maybe some analysis of this approach, right? This sort of integrative few-shot learning approach with this attentive squeeze net is that it allows you to both classify and segment images, and then also to detect a lack of classes of interest. It's able to leverage these correlational features, as I mentioned. And the results of this method show that it outperforms conventional few-shot segmentation tasks. However, you do need, it is computationally expensive. You do need to compute a lot of tensors, and actually you need to insert, you have a fair bit of parameters to learn, right? Which is never great for few-shot learning. And then also you need this expensive pixel level supervision, right? So as I mentioned, if you think back to the sort of figure I showed, in this case, we're assuming that we have these segmentation masks, even in this few-shot setting. So now we're going to turn to the work I'm going to present today, which is being presented by Diane in the audience and other folks on Thursday, which is an update to this work, which looks at the weekly supervised setting. So the question we're asking here is that previous approach required these segmentation masks in the few-shot setting, and what if we can? Is there a way for us to actually avoid that, right? So we're going to look at this. We're going to look at this problem where we're assuming that during training we have access to class labels but not to segmentation mask, right? Which is quite challenging, but here's what we want to do. So it's pretty much what you saw before, right? But in this case now, let's say you have these 3 classes, you don't have any segmentation masks, either for the support images or for the query, but somehow we want to get that, right? So we're going to talk through a little bit how we do that. So in this work, what we aim to do is to leverage attention maps from vision transformers, in particular, self-supervised vision transformers, and you'll see down the line why that matters. We're going to once again use correlation between query images and support images. In this case, we'll be using correlations between tokens from the transformer. And we're also going to explore a mixed supervision approach where we assume that rather than have no segmentation masks at all, or rather than assume we have all the segmentation maps, let's insert a small amount and see what that gives us. So before I get into that, let me just make sure we're all on the same page and very briefly talk through vision transformers. So for those of you who are familiar, vision transformer with regular transformers, which you have a bunch of you tokenize textual tokens, let's say. In this case, with vision transformers, you're basically tokenizing images, right? So you get a bunch of local patches. You consider these patches to be tokens. You vectorize your patches, and then you put them through a typical transformer architecture at that stage. You add to it one embedding, which is a learnable embedding that's meant to represent class-wise information. You run that through a typical transformer architecture. So here we're showing here from the original VIT paper, their architecture, and on the side you see what one of these transformer layers looks like. This whole transformer has L such layers, and then you transform progressively these tokens until at the end you have your final tokens, and then you take your class token and you can do other things with it. But we're not so interested in that. We are interested in this method, which was proposed by Caron et al. In 2021, which looks at a different way to train vision transformers, right? And the goal here was to train vision transformers for downstream tasks. And these authors proposed a self-supervised approach, right? Which you also heard a little bit more about earlier. So their approach was to distill a slow-moving teacher network. So, very much in the paradigm of teacher-student training for self-supervision. In this case, you have the teachers being updated, very slowly, basically with momentum updates from the student weights, right? So the teacher weights are theta t and the student weights are theta s. And the way the loss that's applied is a loss related to matching distributions, probability distributions for latent classes. So just to very briefly go through this, let's assume you have an input image X, right? So this is the self-supervised approach where we have no labels, right? We'd have just images. So we take one image X, we create 2 views of that image. So that could be, for example, different crops of the image, X1 and X2. We run one view, X1, through the student network, right? The student network G was parameterized by theta S. We apply softmax and this gives us a probability distribution P1. We run the view 2 through a teacher network, perform some normalizations, and then we have a second distribution, and then we want to match these 2, right? So this is the self-supervised loss that we are trying to, objective, I should say, that we're trying to optimize for. And what this paper showed is that this learning approach, this self-supervised learning approach, had an emergent property where there were very localized semantics, okay, which was not at all supervised. This was trained from scratch. And this paper and other papers have noted that this is a lot of rich local semantics that can be used for, other things, right? And we're in this, we're going to really try to leverage this to solve our problem, right? Of trying to have a weakly supervised few-shot scenario where we're going to try to get segmentation maps at test time without having any labels whatsoever, segmentation labels. So our approach, once again, I'll go through this in excruciating detail, but just at a high level to start with, our approach, once again, is assuming that we have a query image and a support image, right, to keep it simple for now. What we're going to do is we're going to take a frozen DynoV VIT model, and we're going to get a series of tokens coming out of that, right? So these will be, importantly, not a set of what we call image tokens. So these are localized tokens that correspond to patches in the image. And then we'll have a class token as well for each of this. As you remember, right? We had a set of image tokens, and we had this class embedding that was appended. And what we're going to do is we're going to basically compute correlations between the image tokens of the query and the image tokens and the class tokens of the support, right? And I will go into the detail, not go into details right now of this, but you will see a similar flavor to what you saw earlier with the work by Kang et al. On integrated diffusion learning. So I'm just going to do a quick time check. What time? How much time? Until, sorry? Ooh, okay, thanks. All right. Right, so first let me discuss the correlation tokens that we're going to use, which will be really a lot at the center of this work. So as I mentioned, we have this frozen dino trained VIT. From this, we're going to extract a bunch of image tokens, as I mentioned, and then one class token, right? So we have the image tokens F, which we put into a matrix, and the class token H. We're going to extract these for both the query image and the support image. And then we're going to cross-correlate the image tokens from the query with the class token and the image tokens from the support image, right? And we're going to use this to generate what we call correlation tokens, with the sort of dimensions you see here, which I think help to kind of understand what's going on. And so we described all of this for one layer, right? But as you remember, we have L layers in our VIT, and then we also have, because VIT has multi-head attention, we have M heads per attention layer as well. So we're going to concatenate all of that into this very sort of high-dimensional, very semantically localized, rich matrix or tensor, let's say, that has tokens for every location in the query image, location in the support image, layer, and head, right? So this is going to give you a lot of rich information, which is what we need for our segmentation task. So now, once we have that, let's see how much detail to go into here. So we are going to extract from this, we're going to index over our query tokens, right? So we're going to say for every query token, let's say I here, we're going to look at the tokens we have from the support image, the correlations with the support images for every head and for every layer. And that's going to be our representation of the query token for that region. And then we're going to concatenate that with the class representation for that query token. We're going to concatenate that, and that's going to give us a set of tokens that we're going to input into our correlation transformer, okay? So that means that for every image, every location in the, every patch location in our query image, we have this long tokens for that, and then we're going to input that into our transformer. And this is a small transformer model, like 2 layers. And I won't go into the details of the actual layer itself. I will just note at this point that this is where masking happens, right? So here you see when you have your typical attention mechanism where you have the query, a query here is a bit overloaded, unfortunately. Here I mean query in the sense of an attention mechanism. So we have query embeddings, key embeddings. We do typical multiplication to get our attention matrix. And at this point, before the softmax, we're going to input a mask. And this mask is going to be our segmentation mask. And I'll describe in a second how we actually do that. Right, and so once we have, we're going to do this for all of our query tokens, as I mentioned. And this is going to give us a set of tokens for the regions for the query and, like a specific dimension. And then once we do that, we split that to get features that we're going to input into our 2 task heads. So in the end, we have one task dedicated to classification, one head dedicated to segmentation, and these 2 will be input into those heads to give our final predictions for our 2 tasks. So for training and inference, we use cross entropy losses for both of our tasks and balance it with lambda parameter, a hyperparameter. And then when at inference time, we're going to, let's assume we have an n-way k-shot problem. We're going to average our logits over the k-support images. And then for classification, we will threshold the class responses. And then to segment, we will choose, for a given pixel, right, we'll choose the class with the highest response, subject to a threshold. If no class has a response above a certain threshold, then we assume the pixel is background. Right, so all of what I described there didn't actually talk about how we are generating pseudomasks, right? So in this setting, we don't have any ground truth masks, right? So we're going to have to, we take the approach of generating pseudomasks instead. And so to do that, what we're going to do is correlate, basically, we're going to use the correlation information between our support images and our query images as a sort of pseudo ground truth for our mask. So in the interest of time, I don't think I'll go into too much detail here. I will simply maybe say here that our pseudo masks, which maybe I can try to, yeah. So we do some normalizations here, but I would, no need to look into that too much. Let's just look here at the sort of unnormalized masks. And what we're doing here is we're getting pseudomasks for the support image and pseudomasks for the query image, simply by computing similarities, as you would imagine, right, between the keys of the support image, the keys of the class, the queries of the class token here. And then same thing for so this you can consider it as sort of self-attention. And then here you have a cross-attention between the query image and then the support image features. All right, so what's nice about this is that because we're using intermediate representations from the VIT, right, which we would need to compute anyway, this is introducing negligible extra computation. And in some sense, it's like some sort of self-distillation, right? In the sense that we're using intermediate representation from our own model to give us these pseudo ground truth masks. So that is how so going back to that, right? This is how we construct masks that we're going to use to actually train our model at training time. And so you can say, and you will see that it actually performs pretty well, but of course it's not going to be as good as if we actually had the real masks, right? So what we asked ourselves, as I mentioned before, is given that we're still going to have this gap between image level supervision and pixel level supervision, what can we gain from injecting some small amount of ground truth masks at training time? So we looked at this by proposing this mixed supervision setting where we use some small number of ground truth masks during training. And then we also looked at could we use them to somehow enhance the pseudo mask that we're generating already. And so what we do is we train basically a small enhancer network that takes as input the pseudo mask that I just showed before that we generate using these intermediate representations. And then we actually run them through a network, and then we optimize a network on that small amount of ground truth mask that we have. And so just to show quickly kind of what this does. So here we have a support image and a query image. You see like the dog is indeed relevant in both. So we should actually see the dog be segmented if this was to work well. So here's a pseudomask that we generate for this query image. You can see that it does get the dog, but it kind of gets this fire hydrant as well. And then we see with our enhanced pseudomask, we actually get a pretty decent segmentation that's not too far from the ground truth, right? And here you just see a similar example where you see the boat in both, where in this case, the pseudomask is not great, and then it's much improved after the enhancement. Right, so here, I think I can skip that in the sake of time. So let's go to experiments. So first, let's talk about some model data set evaluation details. So we used, as our VIT model, we used a small version of that. Why? Because that makes it comparable in size, training data, and model performance to ResNet-50, which is what most models, most works in this area do. This backbone has 6 attention heads and 12 transformer layers, right? So that is important because we use that a lot. We use information from all those layers and all those heads, as I mentioned. Once again, so this was pre-trained with the Dino approach on ImageNet, but once again, we didn't, these the folks who trained Dino, they did not use the labels from ImageNet, they just used the images. In terms of data sets, we evaluate on Pascal 5i and Coco 20i, which you've seen already before today, but just like quickly to be sure we're on the same page. This is versions of these data sets where they were to evaluate you for fold evaluation, where you split the data sets into 4 disjoint sets. And then for each of these episodes, we sample, for training, we sample our support classes on the fly, and then we do a next layer of sampling where we sample images from those classes. I won't go into some of those details. I'll just say, like, for evaluation, we use multi-label classification approach metric, the 0-to-1 exact match ratio, and then we use mean IOU for segmentation. So showing some results for image level supervision, we see, first of all, that the model performs comparably to prior work on classification. So once again, the caveat here is that these approaches use ResNet, whereas we use VIT, right? With the hypothesis that VIT is actually going to give us good localized information, especially the self-supervised version. But that being said, like, the classification performance is pretty similar in this case. And then here, maybe what I should do actually is just describe the difference between these two. So in this case, we're looking at a version of our method, which we call CST, with where we don't have this pseudomask, right? And then we have a version where we do use it. And what we see is that, of course, well, I shouldn't say of course, I mean, this is the work. It shows basically that the information from the VIT, right, this localized information is indeed working. It's giving us, it's allowing us to be able to supervise in an effective way for segmentation. And then we see, interestingly, that this actually improves classification performance as well for this task. And we saw these results are for Pascal, but we saw similar trends for Coco. And just to look at some qualitative results, so I won't go to all of the examples maybe, but let's look at this. This is a two-way problem. So we have 2 classes and we have this query image here. So here you would expect that because this is some sort of bird and then there's a bike, and so there should not be anything segmented out, and indeed nothing is. If you look at the ground truth, you see an example where the bus gets relatively correctly segmented out. There's a cow as well. Of course, there are failure cases. So you can see here, for example, the car here gets segmented even though there's no car present in these images. So with mixed supervision, here we're showing results, I think once again for Pascal, where we are looking at what injection of some small amount of supervision does, supervision in terms of segmentation masks. And as you would imagine, injecting some small amount does indeed help, right? So this is if we just throw in a few real masks, right, into our training set, like 5%, 10%, etc. Then we have the results. We include results if we try to enhance these masks, as I mentioned, where we actually include this enhancer module and we improve the pseudomask a bit. And indeed, we see that that does boost performance a little bit, more so when we have a small amount of injected data. And then lastly, we looked at what if we had this, but then at testing time, we actually had ground truth masks for our support images. And then we see that this boosts performance quite a bit, as you would expect, but this is sort of just to test a bit of more of an upper bound. Lastly, well, I think almost lastly, we also looked at pixel level supervision. So what if we had all the data, right? So this is more to kind of test the modeling choices that we made. And we see that performance does compare, we do compare favorably to methods from the literature. And so we attribute that to better modeling, right? The fact that the VIT is indeed, it's a good baseline model, backbone, I should say. And then also that our approach of using this correlation information is actually quite useful. And the fact that we use 2 task heads as well is a modeling choice that we made that seemed effective. And we have an ablation study to show that too. And another thing I think is interesting to note is that if we compare to some prior work, most works, as you know, freeze some parameters and add a few new ones that we have to train, right? And so in our case, we actually introduced a pretty small amount of new parameters, which I, would sort of, we kind of speculate, right, has something to do with this as well, because of course we don't have a ton of data. So the fewer parameters we have to train, the better. And this is just quickly to show that, most of the results we show are with 2-way classification, well, I should say two-way classification and segmentation, but we do see similar results for up to five classes. So here, I just quickly want to show the sort of the segmentation results we can get with different amounts of supervision, right? So I kind of showed this a bit in quantitatively, but just to look at one example, maybe. Let's say we have the support image, two support images here for two classes and a query image. So what we want, right, is to actually segment out this vote, right? That's what we should be segmenting. And here you can see that, here you can see our prediction from a model that only has image level supervision. You can see that here we do indeed get the vote, but indeed also a lot of spurious kind of foreground information, like this sort of poll here. If we introduce 10% of mixed ground truth labels, it cleans it up a fair bit. If we have full supervision, it cleans it even better, right? But you see the difference is not too bad. So in terms of ablations, I don't think I'll go into this for the sake of time. I'll simply just say that we did compare our self-supervised VIT to other alternatives. So for example, what if we use a class supervised VIT, i.e. a fully supervised VIT, or what if we use a self-supervised CNN? We looked at different alternatives and we found that the self-supervised VIT works best, which is really, once again, just confirming prior observations, right? That the self-supervised VIT really does have this emergent property of localized information. And then also we showed, I mentioned before that this having these two separate heads is valuable, and this just simply shows that if we have an alternative modeling where we try to couple the two tasks, it doesn't perform as well. And I think I'll skip that and just go straight to conclusion. So to conclude, we validated this sort of known fact, right, that self-supervised VITs contain a lot of localized semantics for the task of weakly supervised few-shot classification and segmentation. We saw that we can enhance this information via some sort of self-distillation and leverage it for the tasks that we discussed. In terms of future work, so we can think of applying I think self-supervised VIT approaches to tasks with even more expensive labels, because you could argue that segmentation is expensive, but it's not too bad, right? But you can think of places where getting these labels is actually quite expensive, right? And I think that that's quite interesting. We could also think of going beyond cosine similarity for support query alignment. A lot of the sort of juice of this work is in getting these very sort of high dimensional tensors, right? With the correlations between support and query tokens. Can we go beyond that? And then lastly, how can we better combine information from multiple shots, right? So we sort of treat these shots as relatively independent. And so I think there's work to be done there to think of it more jointly. And I think before that, last but not least, I'd love to thank my collaborators, including Diane, who's here, Peter and Minsu. It was great working with them on this. And if you'd like to discuss this in even more detail, you can come see our poster during the Thursday morning session. And with that, thanks for listening. Happy to take questions.